don't care about the damage. We care about the people. Our testing exceeds the government standards. Ford has more 5-star rated vehicles than any other car manufacturer. We go that extra mile to make sure our cars are safe. I'm proud of that. We crash it. We don't care about the damage. We care about the people. We don't care about the damage. We care about the people.
So they don't care about the damage. They care about the people, right? But this car is total shit at 40 miles per hour. 40 miles per hour, guys. That's the fast parking lot speed. You simply did not see the building coming. Why do they make these cars so fragile, so crushable?
Is it safer?
All right, so it's because of safety, right? So how does making a car this fragile make it safer? What's the advantage of it? There's got to be an advantage.
We don't care about.
And why not make cars indestructible the way they used to up until late 1950s?
We care.
All right, so yeah, go ahead.
I was gonna say, I think it's fragile because the object that's inside the car, when the car would stop, the object would keep moving. Isn't that due to like inertia? Because they were both moving in the same speed, and one changed acceleration in the opposite direction. So while the car crushes, the car and the body are still able to move forward and give a little bit more like gradual slowdown instead of just like an instantaneous snapback while you're still moving forward.
All right, Jesus, I'm going to give you 5 points for that explanation. All right, so obviously it's safety, right? So how does that make it safe? Having a car crumple or crush, how does that make it safe? Well, it makes it safe because acceleration is what kills, what breaks your bones. As far as accelerations are concerned, you know you can survive up to 72 Gs for a few minutes. All right, so it's possible to survive up to 72 Gs. Speaking of acceleration, here's what happens to your body. When a car accelerates in the forward direction, your body's going to move in the opposite direction of the acceleration. You put the brakes on. Now your body moves forward when the acceleration is in the backward direction. And then you notice that the unstrapped objects will always accelerate. Unstrapped objects will always move in the opposite direction of the acceleration of the vehicle. So we discussed that. Except when you're inside a centrifuge, when you're exposed to about 7 G, you're not speeding up, you're not slowing down, but you're changing direction, right? So changing direction, how fast you change direction, is that also accelerates? All right, so let's get back to the way we look at acceleration. So pendulum, when the car accelerates in the forward direction, it's going to move backward. When the car is accelerating in the backward direction, the pendulum moves forward. And in circular motion, what happens to the pendulum? Pendulum is going to move away from the center of the circle, meaning that the acceleration is going to be directed towards the center. So now we have a complete definition of acceleration. That's how fast you speed up, how fast you slow down, and how fast you change direction. How fast the velocity changes in time. Speeding up, slowing down, changing direction. Speeding up, slowing down, changing direction. Is going to change velocity. So it's how fast the velocity changes in time. So that's the definition. We'll express acceleration in terms of your own body weight. So your own body weight is the same as 1 G, for example. Being exposed to 7 G simply means you're feeling 7 times heavier. Or you will feel a push in the opposite direction of the acceleration of the vehicle, expressed in terms of your own body weight. Now, acceleration is always going to point in the direction of the larger of the two velocities. Right? If it's to the right, in this case, the car is speeding up. So positive acceleration means speeding up, and negative acceleration means slowing down. So you can have positive acceleration or you can have negative acceleration. Positive in this case is speeding up, the negative is slowing down. All right.
1950s, years before.
So 70 to 12 Gs, up to a few minutes, are survivable. Car companies wanted to know if you could survive 20 Gs, 30 Gs, 40 Gs, 50 Gs. What is the maximum that you could be exposed to and still be able to survive? So how do you figure that out? By testing real quick.
For the Pinto or Corvair, little was known about the essence of a collision, how much force the driver could withstand. To find out, a seemingly lunatic experiment was carried out in the New Mexico desert by the U.S. Air Force in 1954. Scientist John Stapp strapped himself onto a rocket sled to boldly go where no man had gone before.
He started the countdown. 10, 9. Adrenaline comes in and the heart begins to beat a little faster. Then just as he reaches 0, you get this enormous ram against your back and you feel totally helpless. You'd be given the biggest kick that could be delivered.
Stapp had been propelled at a speed of 632 miles per hour and stopped in 1.4 seconds.
All right, guys, 632 miles per hour. It was brought to a stop within 1.4 seconds. 632 miles per hour. 632 miles per hour. How fast is that? Commercial airliners move at 550 miles per hour. This guy was already moving 30 miles per hour faster. No, 80 miles per hour faster than commercial airlines. It was brought to a stop within 1.4 seconds. 1.4 seconds. Now imagine that you're on this airliner, doing whatever it is that you guys do, going at 632 miles per hour, and you're brought to a stop within 1.4 seconds. What would that feel like? So that's what the car companies wanted to find out. All right, so I've done the calculations for you. Right? So he's already moving at 632 miles per hour. All right, so this is his speed, and he was brought to a stop within 1.4 seconds. So what is his acceleration expressed in terms of speed? All right, so here's the formula. This is the formula. His final speed is going to be 0. And then you run the numbers, and you end up getting 20 Gs. All right, so you end up getting 20 Gs. It's negative, meaning that he's actually slowing down. So the question is it survivable? Can you survive 20 Gs? Let's check to see what happens.
No one has ever undergone such a test before or since.
I couldn't see anything, and I was looking around, and
While he's alive,
you
he did survive 20 Gs.
didn't think about seeing eye dogs and white canes.
Well, he couldn't see anything because his retinas got detached. Is that a big deal? Not really, guys. If your retinas get detached, just push him back and check to see if that works. If it doesn't, they'll take you to a hospital. And if you don't recover, there's usually a surgery awaiting you. Happens to boxers sometimes.
And I was thinking to myself, now I've paid my dues. I've gotten there. And I've shown them what they want to know. And from now on, life is going to...
No one knew whether he was going to die or survive. Why would you volunteer for someone? They advertised, no one was interested. John Staff, this guy is a medical doctor, who was in charge of the experiment. He conducted some experiment using animals, cats, dogs, rabbits, whatnot. They were fine. He figured that he was going to be fine as well. So he did survive up to 20 Gs for 1.4 seconds. 1.4 seconds. So that's survival. And that he kept doing the experiment time and time again, only to realize that, yeah, you can actually go up to 25 Gs easily without sustaining any injuries. After 25 Gs, you start to have problems. Smaller bones in your body will start to break. So between 20 and 25 Gs, up to a few seconds, you should be able to survive. So these are big numbers. So 7 to 12 Gs, up to a few minutes. Big fun. Pilot training in a centrifuge. And job step experiment proves that you can survive between 20 to 25 Gs, up to a few seconds.
The Mercedes S-Class is one of the biggest and strongest cars in the world. It's also one of the safest. But in Paris, on August 31st, 1997, this car was involved in the most notorious car crash of all time. The Mercedes was carrying 4 passengers, a chauffeur, a bodyguard, the Princess of Wales, and her boyfriend. They were reportedly speeding away from photographers when their car approached a narrow underpass. Professor Murray Mackay is Britain's leading car crash investigator. Using official reports from the French police investigation, he's reconstructed what happened.
According to the accident investigators, this is where the accident began. About 20 past midnight, the Mercedes is coming along this road on the left bank of the Seine towards the Alma Bridge. It heads down towards the underpass, and it's estimated at that time it speeds about 70 miles an hour. What happens next is based on the evidence that we have so far. As he comes down into the tunnel, he's faced with a slow-moving Fiat. He steers to the left. Because he's just come over a crest, the steering's light, he probably puts in too much steering, so he's heading towards the center columns. He corrects right, and now he's heading directly for the Fiat Uno.
According to police reports, the Mercedes sideswiped the Fiat, but the only damage so far was a broken mirror and a smashed taillight.
Was the Fiat just an innocent motorist returning late at night, or was there something more sinister than that? We may never know. The French police have given up the search for that vehicle. What we do know is that at this time in the accident sequence, the actions of the driver of the Mercedes were not those of somebody who was normal and alert.
A 106-foot skid mark shows the Mercedes driver pulled the steering wheel back to the left. The car jumped the pavement and smashed head-on into column 13. The car spun around and ended up facing in the direction it had come from. Mackay thinks the Fiat drove by without stopping.
Speed, a driver under the influence of alcohol, the unexpected encounter with the Fiat, these all played their part. But you must remember that from the time the car entered the tunnel until it came to rest after the impact, that's only about 2 seconds. Newspapers have talked luridly of speeds of 120 miles an hour, but looking at the damage tells a very different story. It suggests an impact with the pillar of about 60 miles an hour. And we know that the car came to rest about 15 feet from the pillar, spinning out, and that means about 10 miles an hour exit speed from the pillar. So the change in velocity was slightly less than 50 miles an hour. And it's that change in velocity which is crucial in terms of the severity of the crash to which the occupants were exposed. This was a severe but a survivable accident, and what we now need to consider is why did 3 people...
So he thinks that this is a survivable act. Is it really? Do you think this is survivable?
And it's that
If you're driving by
change in
and if you see a car
velocity which is crucial in
this badly damaged,
terms of the severity of the...
are you thinking to yourself this is survivable? What do you think?
No.
No, right? I mean, you're driving by and does it surprise you that there are 4 people in this car and 3 of them are dead? No, right? It makes perfect sense. You look at the damage and you say, yeah, that makes sense. It doesn't seem survivable.
Who's the only person that survived in that crash? What side of the vehicle were they on?
All right, the only person who survived was the bodyguard. And the bodyguard was sitting up front, obviously, on the passenger side. And he was the only one to survive. All right, so, all right, guys, here's the difference between me and you. I'm driving by, I see this, I go, okay, perfect, this is survivable. Car did its job. The car is designed to crumple. All right, you want the car to crumple as much as possible. What's surprising is 3 out of 4 people are dead. It's not supposed to happen. Why is it that I'm so confident that this is survivable? And why is it that this guy is so confident that this is survivable? This has to be survivable. They make the car crushable so that you can survive them. All right, so let's go back to the number.
After the impact, that's only about 2 seconds.
So it takes 2 seconds to get to the 13th floor. And then the impact. Estimated initial speed. The impact is.
Newspapers have talked luridly of speeds of 120 miles an hour, but looking at the damage tells a very different story. It suggests an impact with the pillar of about 60 miles an hour.
So initial speed is about 60.
And we know that the car came to rest about 15 feet from the pillar, spinning out, and that means about 10 miles an hour.
Final speed is 10 miles per hour. So what's the change in velocity here? The initial velocity is 60, the final velocity is 10, so what's the change in velocity? It's 50 miles per hour, right? It's like crash test.
Exit speed from the pillar.
All right, so the only thing we need to know at this point is what is the impact time? Where do you get the impact time from? Impact times are built into these vehicles. You get your impact time from the crumple zone, crumpling of the car. It's going to give you your impact time. It's about 10th of a second. So at 40 to 50 miles per hour, impact time is about 10th of a second. So within 10th of a second, the car goes from 60 miles per hour to 10 miles. So what is the acceleration? All right, so the acceleration in this crash, and I've done the calculations for you. All right, so change in velocity is 50 miles per hour within 10th of a second. That's 22 G. Right? That's survivable. What do you think? Yes or no? Can you survive 22 Gs for 10th of a second?
Yeah.
How do we know that? Jan?
Because in the last experiment, you said that a person could survive up to 25 Gs.
Right, I'm going to give you 5 points. Absolutely, right? John Stat was able to survive that. Up to 1.4 seconds, guys. That's up to 1.4 seconds. That's a duration which is 14 times larger than what this car is exposed to. An old guy was able to survive it. Same sort of force, same sort of G load for a duration which is 14 times longer than what these people were exposed to. And he survived just fine. His breath now got and then he recovered. Yet you have 4 people in this car. 3 of them are dead. One of them, the bodyguard, he's the only survivor, and he survived barely. What went wrong? It's not the car's fault. These people must have done something that they weren't supposed to. Does anybody know what the problem was?
Maybe didn't wear their seatbelts.
Say it again? Seatbelt. Give yourself 5 points.
Strangely, Princess Diana, sitting where I am in the right rear, had the best chance of survival because the impact was concentrated on the left front of the car, and as it hit the pillar, it also rotated and span out, so she went partly past the pillar and didn't have quite the same crash forces applied to her as happened to the people sitting on the left. If she'd been wearing a seatbelt, she'd have had a fair chance of surviving even this
So she wasn't wearing a seatbelt.
extreme accident.
And who cares?
But, unbelted, she was thrown forward.
Who else was not wearing a seatbelt that day? Her fiance, sitting next to her. He wasn't wearing a seatbelt either. Who else wasn't wearing a seatbelt? Driver was not wearing a seatbelt either. The only person who was wearing a seatbelt was the bodyguard.
To strike the back of the front
And the bodyguard was seated right here.
passenger seat.
So she lunges forward, hits the back of the front seat, and then back of the front seat brakes. Bodyguard launches in the forward direction, smashes his head against the dashboard, and he has no recollection of what happened. No recollection. He was in a coma for about 2 weeks.
Door pillar,
And he's the only survivor.
and then was tossed around after the main accident took place and the vehicle span out.